All right, cool. We're going to start where we left off last time. We left off talking about polyatomic ions. We had this kind of small list that we said that we just got to know here, and we're going to continue to build from there. All right, so again, these are our polyatomic ions. We have to know. Okay, so there are two that are kind of unlike the rest of the group. So I'm going to put them in their own little category here. The rest of them kind of follow a similar pattern. So the first one was that OH with a -1 charge. Everybody take a second and see if you can't remember what the name of that polyatomic ion was. That was one that we went over. Right, so that's the one that we sort of maybe are even familiar with from our previous chemistry courses because it's such a well-known base that's used all the time. This is the hydroxide ion. All right, again, we can just make a note of sort of why it's special and why we want to keep it in our mind here because it is a strong base. You know, there are truthfully quite a few strong bases out there in the chemistry world. This is by far the cheapest and easiest to use, safest to dispose of, et cetera, et cetera. So it's really the go-to base in chemistry, okay? The other one we're going to kind of put in this weird category here is NH4, and this one has a +1 charge, okay? This is what's known as the ammonium ion. And the ammonium ion we want to sort of make a special note of because there's something really weird about the ammonium ion, and that is the charge of this polyatomic ion. All of the other polyatomic ions that we covered were anions. This is the one polyatomic ion that we're going to study that is a cation, that has a positive charge associated with it. All right, so let's just note it's the only positively charged polyatomic. Truthfully, I think in the world there's like 2 others, but we're not going to study those. Again, very, very rare to have a positively charged polyatomic ion. All right. So again, we said that this was a cation. Remember, that was a term that we used for positively charged ions. All right. The other thing that makes ammonium really weird is what were all of our other cations that we learned in terms of where they lived on the periodic table? We had this little staircase dividing line here. Which side was the cations living on? Over here, what kind of elements were those? Metals, right? Okay. Nitrogen, hydrogen, are those metals? No. So this is not only the only polyatomic cation that we're going to study, it's also the only cation that we have that consists of only nonmetals. All right, so okay, so these two here, we're going to kind of put in this weird outlier category. We got to know them, but they don't quite follow the same pattern as we're going to see with our other polyatomic ions. Okay. So I'm going to now, so we're going to introduce a few that we've already studied as well as a few new ones. And I want to organize this on this nice little table here. All right, so what we're going to do is we're going to create 4 rows and 3 columns. Okay. So we're going to fill in this side over here with the polyatomic ions that we discussed last class, the other group of polyatomic ions that we discussed. If you remember, the very first one that I introduced was this polyatomic ion called the nitrate ion. Okay, and that was that formula NO3 with a -1 charge. We introduced quite a few that had that ATE ending. That is what this group is all going to share. All right, so I want you to dig in your brain here, complete this table with the names or formulas of these polyatomic ions. So nitrogen in this polyatomic ion, that was a nitrate. What about carbon? Carbonate. And what about with sulfur? Sulfate. So now this one I gave you the name. Remembering the formula is quite a bit harder. Obviously phosphate's going to have a phosphorus. They all have oxygens. The question is how many oxygens? In the case of a phosphate ion, there are 4 of them. And then importantly, what is the charge on that polyatomic ion, right? Those are the kind of the 2 difficult things we got to remember for these. A phosphate ion has a -3 charge. Okay, so now we're going to learn a new set here. And they're going to be very similar to this existing set here. In fact, if we have this memorized, it's really easy to figure out what these other ones are. All right, so we're going to first play the spot the difference game. I'm going to put down the formula here. This next one is NO2 with a -1 charge. All right, what do we see different about the formula between this and our existing one that we had? We got 1 less oxygen, right? 1 fewer oxygens. Importantly, and what I really want you to take note of, is that the charge is the same for both of these, okay? The charge doesn't change. We just decrease in number of oxygens by 1. All right, so in this category, what we're going to see is this pattern where we decrease number of oxygens by 1. And when we decrease the number of oxygens by 1, our polyatomic ion goes from being the nitrate ion to the nitrite ion. Decrease by 1, and we're going to replace that ATE with an ITE ending. All right, now, it turns out that there's no such thing as a carbonite ion, so we're just going to skip this here. But I want you all to see if just by analogy with what we just did, fill in these remaining 2 squares here. All right, so it was SO4, 2 minus. Now it's going to be SO3, 2 minus. And instead of sulfate, this is sulfite. So the next one, instead of being a phosphate ion, it's going to be a phosphite ion. How many oxygens does a phosphite ion have? 3, right? One fewer than a phosphate, but again, that charge is the same. Okay, so then the last category here is actually ones that we've already studied as well, but I just want to put them next to this group here because they do sound sort of similar. These were all of our polyatomic ions. All right, but when we actually first were introducing ionic compounds, the first set of ions that we introduced were what were called monatomic ions. What the heck does that word mean, monatomic? One atom, single atom ions. So for example, and I would strongly suggest that you kind of always go back to this one example that you just kind of instinctually know when you're trying to figure out your nomenclature and stuff. NaCl, I think we all know is salt, but the chemistry name is sodium chloride, right? So remember, that Cl with a -1 charge, that was a chloride ion, okay? So, when we first learned about ionic compounds, we said nitrogen. We can just look at the periodic table and tell what type of ion nitrogen will form, okay? Let's look at our periodic table here. Ignore this, not this class. Based on the periodic table here, what types of ions does nitrogen like to form? What charge? -3. Remember, the noble gases, they don't form ions. The halogens, -1. Oxygen's column, the chalcogens, -2. And nitrogen's column, -3, right? So we learned just by looking at the periodic table, we can figure out these charges. And so if I have nitrogen all by itself, what is the name of that ion? Nitride. All right, so we got all these very similar sounding compounds, rather ions, so we're gonna line them up next to each other so we can make sure to keep track of what's what here. We have our monatomic ions that end in IDE, and we have these polyatomic ions. When they have a bunch of oxygens, they're 8s. If we decrease the oxygens by 1, they're ites, okay? So again, I want you to fill in the rest of this table here. It turns out that there's no such thing as a carbonide ion, so you should be able to fill out sulfur and phosphorus as monatomic ions here. When sulfur forms an ion, what is its charge? -2. And so this would be a sulfide ion. When phosphorus forms an ion, it lives in the same category as nitrogen, so it also forms a -3 ion, and this is a phosphide ion. All right, so these are the group of polyatomic ions that we just have to know, as well as these two kind of weird standalone ones here, the hydroxide ion and the ammonium ion. You can probably see now why I put them separately. They don't follow these same patterns. All right, but we have these polyatomic ions that we have to know. If we decrease this category here, right, if we decrease the number of oxygens by 1, we're going to replace that ATE ending with an ITE ending. All right, and then just for completeness, we stack them next to their monatomic counterpoints, or rather analogous compounds, so we can see the similarities and the differences here, right? So we don't get them confused. Cool. All right, so we're going to sort of switch gears and start talking about covalent compounds here in a second. But before we do that, and we're sort of rather how we're going to segue into that, is we're going to look at the structure of these two different types of compounds. All right, so by that I mean the structure of ionic compounds and how they compare to the structure of covalent compounds. Okay. All right, so for an ionic compound, we're going to take our favorite go-to here, sodium chloride. I'm going to picture the sodium ion in orange, so that's going to be an orange dot, and the chloride ion in green, so that's going to be a green dot in my structure. I'll put a plus and a minus sign so we can remember who's who. Sodium's the positively charged ion, chloride's the negatively charged ion. All right, so when you have a sample of sodium chloride, you never just have one pair of sodium ions and chloride ions. Ionic compounds don't exist like that. You always see them in what's called large arrays of ions, meaning repeated units of positive, negative, extending out forever, right? So the structure of salt, if you were to hop into your magic school bus and zoom on down, you would see your positively charged sodium ion, then your negatively charged chloride ion rather, and then it would just continue to repeat. Okay? But not only does it repeat in one direction, it's not like they all sit in a straight line, it's going to repeat in 3 dimensions, right? So there's also going to be a plane of atoms going this way. As well as into the page, which I feel like if I start trying to draw, it's just going to look absolutely crazy. But right, you just see a whole sort of array of these positive and negative ions all stacked next to each other. Okay, so this is kind of the picture what we want to have in our mind of our ionic compound. It's never just one positively charged ion and one negatively charged ion. That's not how you find them. You always find them in big arrays. Okay, so an example of ionic compounds that you find in nature are rocks, for example, right? And if you were to zoom on in, you would just see this repeating array of positive and negative charges going on forever. Okay, each one held together by that opposites attract interaction, that electrostatic interaction, but again, never found just all by themselves. Okay, this is different than covalent compounds. So for example, a covalent compound, again, all nonmetals, something like CH4. Okay. What we have with CH4 is we have our carbon atom in the middle. The hydrogen atoms are all bound to that central carbon atom. But this is kind of its own package deal here. Neighboring molecules of CH4 are floating around independently of that other molecule, right? So a covalent compound is kind of like a distinct cluster of atoms that is separate from all the other distinct clusters. So these carbons and the hydrogens are covalently bound to one another, but they're not interacting with their neighbors through covalent bonds. They are interacting in some way, and we'll talk about those interactions when we get further into the course, all right? But again, covalent compounds are like these clusters of atoms that are all covalently bound together, We don't see the same repeating array that we do with our ionic compounds. All right? So these distinct little entities right here are called molecules. You will sometimes hear covalent compounds referred to as molecular compounds for that reason. The sort of analogy or analogous term for ionic compounds, they don't call them molecules, although you will hear this misnomer quite a bit. This little individual repeating unit is what's called a formula unit. Okay, so because of this, we have this sort of different rules for constructing our covalent compound formulas as well as naming our covalent compounds. So covalent compound formulas. All right, let's just take two random nonmetals, the two that are famous in sort of an organic chemistry course, so you'll kind of see them a lot in chemistry, are carbon and hydrogen. All right. Remember, for ionic compounds, our subscripts had to be fully reduced. For our covalent compounds, these can be any number. They can take on any value they want. There is no rules to it. All right, now truthfully I'm lying to you a little bit. There are some rules in nature, but in terms of the naming of compounds and in terms of constructing these formulas, there aren't. So for our purposes, they could be anything at this point. All right? Meaning that you could have something like CH4 that we just saw, but you could also have C2H2. Both of those are perfectly legal. Right? Because again, our covalent compound formulas, they don't follow the same rules as ionic compound formulas. Ionic compound formulas had to be fully reduced. That's not the same for our covalent compounds. So these are both perfectly okay. Okay? So there's no way to look at the periodic table and say, hydrogen and carbon, I know what that formula is going to be. Both of these molecules exist, all right? So we don't have the same sort of way like we did with sodium and chlorine. We could figure out what that formula is. We don't have the same deal for our covalent compounds. Could be anything, all right? So because they could be anything, we will build what those subscripts are into the name. And let me just show you what I mean by that using an example that I think that we all know, which is CO2. What is the name of this molecule? Carbon dioxide. Okay, let's look at what's similar real quick. So first of all, the first element in my formula, I didn't change that name at all. It's just carbon. The second element in my formula, the oxygen, does still have that IDE ending. All right, but now we have this new component to our name that we haven't seen before, this prefix. And what does that di tell me? It tells me that there are two oxygens in that molecule, right? Another one that you may know that's super terrible for you and it doesn't have any odor, so we all have little detectors in our homes, so hopefully we don't get poisoned by it, is what? Carbon monoxide. All right, so I can't tell by the periodic table how many carbons and oxygens are in our formulas here. Both of these are perfectly legal. All right. Again, we have that carbon name didn't change. IDE ending on the last thing. And now we have this prefix mono, indicating that there is only one oxygen in that formula, right? So again, these subscripts can be any number. So what we do when we name our covalent compounds is we make sure to build what those numbers are into the name, because otherwise you wouldn't know. Cool, so we got some prefixes to work with here. We're gonna make a little prefix cheat sheet here. And up at the top, we're going to make a note so that we don't get confused, because this is the big mistake that everybody makes, is these prefixes are only for covalent compounds. Notice how we didn't use a mono or a di or a tri anywhere when we were talking about our ionic compounds. It's only for the covalent compounds that we will use these prefixes. All right, cool. All right, so first we're going to make one column with our number, the second column with the prefix, okay, cool. We said that 1 was the prefix mono, 2 the prefix di, 3 is tri, 4 is tetra. All right, the other ones might be familiar from your geometry class. What do you call a 5-sided polygon? A pentagon. So yep, so 5 is a pentagon. Oh, no, not a pentagon. Is a penta, the prefix. 6 is hexa. 7 is one that not a lot of people know. 7 is hepta with a P. 8, what is the shape of a stop sign? Octagon, so 8 is octa. 9 is nona. And 10 is deca. And we're going to stop there. That's good. All right. Truthfully, there's a whole system that, I think you can put together any number. This is going to be good for right now. Okay? So here are our prefixes. And let's just lay down some simple rules for naming our covalent compounds. Fortunately, this is way easier than naming an ionic compound. Okay. The first element in our formula just like in our example compound carbon monoxide, you don't change the element name. Okay, it's just going to be whatever it says on the periodic table. Okay, the other thing to note from our example here, this second one was carbon monoxide. The mono indicates that there's one. But it wasn't monocarbon monoxide, all right? So if there's only one of those first elements, you're going to leave off the prefix. If there's more than one, you do have to include the prefix, all right? So we're not going to touch the name at all, and we're going to only include the prefix if there's more than one of them. right, now for the second element in our formula. All right, again, going to our example, carbon dioxide, we put that IDE ending on the second element. So we're going to again use that familiar IDE ending. It's called a suffix. We're going to be fancy. All right, so we got to use that IDE suffix. And for the second element, you always use a prefix. Regardless of if there's just one or more than one, you're always going to include the prefix. So we always use that prefix. Cool. All right, so let's practice this. I'm going to put down some names. You're going to give me the formula. I'm going to put down some formulas. You're going to give me the names. All right, so disulfur tetraoxide. All right, so sulfur, how many do I have? Two. Oxygen, how many do I have? Four. All right, so disulfur tetraoxide. Okay. Going to name for formula for the covalent compounds is kind of best case scenario. It's pretty straightforward. It tells you exactly how many there are in the formula, nothing crazy that you got to do. All right, N2Cl6. What's the first word? Dinitrogen, right? So we're not going to change that element name, just nitrogen. All right, and then the last one, hexachloride. All right, again, the name to the formula, pretty straightforward. Triphosphorus means that there's 3 phosphoruses. Octabromide means that there's 8 bromines. All right, and then the last one, what's that first word? Pentaiodine. What about the second one? Monoxide, right? We always got to include the prefix for the second element, even if there's only one of them. So this would be pentaiodine monoxide. Cool. All right, we got one more to cover, but before we sort of go there, let's just take a second and rewind. We had started last time by talking about how we could get the formula for our covalent for our ionic compounds. So let's just practice that again. Remember, I said I'm going to give you 2 elements. In this example, we're going to do barium and phosphorus. And you're going to tell me the charge on the barium ion and the phosphide ion. And then you're going to give me the then you're going to give me the formula. And finally, the name of that compound. Okay. I'm going to do these 2 examples for me. They're going to be pretty similar, so I want to put them side by side. And real quick, one mistake that a lot of people made now that we were just talking about covalent compounds. Remember, what did we say about this table of prefixes? Only use it for covalent. So we shouldn't have any prefixes with our ionic compounds, right? That is people on an exam, they're naming ionic compounds correctly. They get to their first covalent compound and all of a sudden everything after that has a prefix in it. It's like, no, don't forget the very first step. You got to figure out what type of compound you're talking about. Cool. So remember, we go to our periodic table. We got to hunt for Ba. Ba is barium over here in this column of +2 ions. Phosphorus lives over here in this column of -3 ions. +2, -3. When we get our formula, remember we learned the easy way to do our formula, this little swap method. This number is going to come down here. This number is going to come down here. So Ba3, P2. All right. Now we got to name this compound here. Is barium a type 1 or a type 2 ion? Right? What the heck do I mean by type 1, type 2?
It's
Yeah, if I got to use the Roman numerals, right? So there's certain elements we got to use the charge in Roman numerals, other ones we don't. Barium is a type 1, meaning no Roman numerals. Right, I can tell that because it lives in the first 2 columns on the periodic table, where I get to know its charge just by looking at the periodic table. Because of that, I don't have to include the charge in the name, just the element name, barium. And then the P with the -3 charge is phosphide, right? IDE ending when it's all by itself. Okay, and I just wanted to do this example because it was pretty similar. Obviously, we established barium has a +2 charge. What about this PO4 business? What's the charge there? -3, and how do we know that? Because we just got to know it, all right? Because it's on our list of the ones that we just got to know. It's always going to be -3. You never see PO4 with anything else. It's not like it's going to change, but we just got to know that PO4 is -3. So when we do our name, we're going to do the same cross method here. The charge comes down. One big mistake, let me just point out, I'm not touching this 4. This 4 isn't the number that's going to come down. Remember, we talked about how this PO4, you got to treat it like a package deal here. You're never going to mess with that formula there. All right, it's the charge that I bring down. So then I'm going to, so BA3, PO4, and I'm supposed to have 2 of them. So how do I indicate that I have more than 1 polyatomic ion? Parentheses. Awesome. Boom. Cool. And so this wouldn't be barium phosphide, but barium phosphate. PO4 is the phosphate ion. Okay, so cool. Just to remind us real quick, because now we're going to talk about a special class of ionic compounds known as hydrates. Okay, so some salts, some ionic compounds will actually absorb water, whether you add water to them or it's just absorbing water molecules from the air, and we call those hydrates. All right, so a hydrate is an ionic compound. That has bound water molecules. Okay? And what's crazy about these hydrates is they always will absorb a fixed number of water molecules. All right? It's like those water molecules kind of fit perfectly like puzzle pieces around these ionic compounds, and there's only a certain amount of puzzle slots. So a particular salt will absorb a fixed number of water molecules. It's always the same number, okay? So let me show you what I mean. We have this special way of writing this. All right, so for example, sodium sulfate is one of these compounds, and we would write its hydrate dot 2H2O. All right, so this is the formula, the chemical formula for a hydrate. All right, and what this is telling me is that that sodium sulfate, that formula unit, will bind 2 water molecules to it. All right, and that's reproducible across that whole, remember we said that they're like these repeating networks of positive and negative charges. It's like there's 2 water molecules for every little group of positive and negative charges you have, right? A set number. So if we want to pick this formula apart for our hydrate here, it's always got the same few components. First of all, we just have our ionic compound formula. And then we have this little dot in the middle here. And everybody's like, oh, from math class, I know what that dot is. That's a multiplication symbol. It absolutely is in a math class, and that is 100% not what it means in this formula right here, all right? All this little dot means is it's a hydrate. It is a symbolism that's unique to hydrates. You will only see it in formulas for hydrates, and it's just telling you that your compound is a hydrate. All right, and then we have a set number of water molecules. In this case, 2. If we were going to name this compound here, we start just with the name of our ionic compound, which is sodium sulfate. Okay? But then when we include that water, those water molecules, we would add on to the end here sodium sulfate dihydrate. Okay. We always just use the word hydrate, but then we stick this prefix out front to indicate how many water molecules they are. All right? Cool. So then what we're going to do is we're going to go back up to this prefix here where I said only covalent compounds. We're going to say only covalent compounds and hydrates. So we use this same list of prefixes for our hydrates as well. All right, so let's try another one here. I'm going to give you the formula. You're going to name it for me. Okay, we'll leave this example up here. This one is LiF6H2O. Got 6H2O. All right, is lithium type 1 or type 2? Just type 1, so it's not going to have any Roman numerals. This is just going to be lithium fluoride. I don't remember if I pointed this out last time, but let me just make a note here. One of the most common spelling mistakes is people really want to say fluoride. Fluoride and fluoride are different, right? F-L-U-O, not F-L-O-U. All right, so just watch out. Super common spelling mistake with fluorine. And it's not just lithium fluoride, but lithium fluoride hexahydrate. Cool. All right, so now we're just going to mix everything up and practice it here. All right? I'm going to put down a bunch of names. You're going to give me the formula. I'm going to put down a bunch of formulas. You're going to give me the names. So, strontium sulfite. Remember, we got to first decide whether this is ionic or covalent. All right, because that's going to determine how we put it together. What do we think? It's ionic, right? The giveaway is the presence of that metal, that strontium metal. So then when we're putting together our formulas for our ionic compounds, it's all about the charge. Strontium lives in that second column on the periodic table. And so you'll always see me when I do this, I'm going to draw out the ions with their charge. Because again, it's all about the charges. All right. What is sulfite? Yeah, so that's one of our fancy ones, right? Not just sulfur all by itself, but one of our polyatomic ions. So this would be SO3 with the -2 charge. And when I put these together and I do my cross method, I get SR2, SO3, 2. And am I done? No. Remember, what do we got to do for our ionic compounds? We got to fully reduce it, right? So those 2's, those are both the same number. So we're just going to cut that all together, leaving us with just SRSO3. Boom. Final answer. Okay. Now this next one, ionic or covalent. Kind of a giveaway because of those prefixes there, right? But you could also convince yourself they're all nonmetals. So dinitrogen means there's 2 nitrogens. Dioxide means there's 2 oxygens. Do I then go and reduce this formula? No, those numbers can be anything they want for covalent compounds. So you're done there. Don't make it more complicated than it needs to be. Okay. And lastly, we'll do this one, the last sort of word to formula here, name to formula here, chromium 2 sulfide. So first of all, that 2 is telling me the charge on my chromium ion. And sulfide, different from sulfite, sulfide is the monatomic sulfur ion. I clearly was very creative with my charges here because we're going to play the same game as before, where we're going to do our cross method and they're both 2's, so that's going to simply reduce to just CRS. Okay? But for those for those transition metals, those type 2 ions, remember that Roman numerals in parentheses tell you the charge on that ion. All right, so now if we're going to go name to formula here, this is where we got to be really careful with our whether it's covalent, ionic type 1, or ionic type 2. All right, so what about this one here? What do we think? Oh, shucks, my bad. I was going too fast. All right, right, so, sweet. Yeah, we got the chromium sulfide down. What about this part? What does that mean? Yeah. 5H2O. Yeah, that was the whole point of that example. My bad. All right, so yes, chromium sulfide, pentahydrate, so CRS dot 5H2O. Okay. All right, my bad. Whole shtick again about the importance of covalent ionic type 1, ionic type 2. Which one is this one? So let's see. Who thinks it's ionic? Who thinks it's covalent? Yeah, so we got our covalent compound here. And so covalent, meaning I'm going to use those prefixes. Tetra, sulfur, pentachloride. All right, what about this one here? Is it ionic or covalent? And is it type 1 or type 2? This would be our type 2, which means that we do have to include those Roman numerals. All right, and this one's going to be a pain in the butt because that means that I have to figure out what the charge is on that iron. All right, I'm going to give myself a little bit more space. Whoops, that didn't do it. Okay, so the problem here is that I do not know the charge on my iron ion All right, so we're going to have to use what we do know, which is the charge on my anion. We know that we have a nitrate ion here, not just one, but two of them, according to my formula. And this is something we just got to know. What is the charge on that nitrate ion? -1. So if we got two of them, what's the total amount of negative charge? -2, all right? And why this is going to help us out is, remember, the basic rule of these ionic compound formulas is that they have to sum to 0. So if I have a total amount of negative charge of -2, that means that's got to be counterbalanced by that charge of +2, and that charge must live on that iron ion. Okay? So when we name this compound here, we're going to include that charge, iron 2, and I think I probably already gave it away, but this is a nitrate ion. So iron 2 nitrate. Okay? So the last one that I kind of threw up there, I wanted to do this example in particular because it's a little bit tricky here. All right? Because you're going to look at that and you're going to say, well, nitrogen's a nonmetal, and hydrogen's a nonmetal, and chlorine's a nonmetal, so this must be a covalent compound. But that NH4, we just got to be able to spy as a very important polyatomic ion. Our only cationic polyatomic ion, the ammonium ion. So this isn't nitrogen, tetrahydrogen, monochloride, or anything crazy like that. This NH4 combo kind of has to jump out at you, and you say, nope, that is ammonium. So this is ammonium chloride. Okay, so again, we're just going to kind of put a little warning label on this one and just say beware. This one is not covalent. Just a super easy mistake to make. Cool? All right. Y'all actually worked yourself a little bit ahead of the other